In this video, we're going to learn about differentials and marginal analysis. In this specific video, we're going to start with differentials and then we'll come back to marginal analysis in the second video. First, I want to bring to your attention dy dx and the limit definition of our derivative. And that's what I have written right here. That's our limit definition of our derivative. It's the derivative of y with respect to x. These two values right here, dy and dx, they represent two separate quantities. They are indeed two separate quantities, which makes them a fraction, a ratio, a comparison, a division problem of two separate quantities. And we call them the differential of y and the differential of x. First, we have to have a function y, which is a differentiable function. So we're first going to be dealing with differentiable functions. So once we have a differentiable function, the differential of x is denoted by dx. It is any non-zero real number. So it can be any non-zero real number. The reason it can't be zero is because it happens to be located in the denominator. So because this is a comparison of two quantities, you cannot compare and divide by a value of 0. So dx is any non-zero real number. And the differential of y is denoted by dy. And it is equal to the derivative times dx. Coolest thing since sliced bread. So I'm going to show you where this is coming from. We know dy dx is equal to the first derivative. If I take both sides, because dx is a quantity, I can take both sides, multiply by dx. On the left-hand side, the dx's cancel out, and I have dy equals f prime of x times dx. It's a beautiful thing. So let's talk about this curve that we have going on here, this graph. So we've got this differentiable graph right here, right? And I've spaced out my delta x so that I can write in here and you can see what's happening. So I've got, I'm going to have to be creative here with the colors. Okay, so I've got x, f of x, right? And then I've got x plus delta x. X plus delta x, that's going to be your input, x plus delta x. And then the output is going to be f of x plus delta x. F of x plus delta x. And these ordered pairs are really important because I do a lot with ordered pairs, right? We could find the slope between 2 points. We're talking about our tangent line, lots of different things that we can do with ordered pairs, but since we're on a coordinate plane, you've got an x coordinate and a y coordinate. Now I'm going to, let's do this in orange. So we've got x as our input and then f of x as our output. So we've got two ordered pairs here. Let me change that. Oh, you know what? I'm going to keep that orange. That's fine. That's fine. That's fine. That's fine. Now, remember that we have a secant line. So I'm going to draw a secant line. Oh, couldn't have done any better if I used a straight edge. So we've got that secant line. And that secant line, look at this. That's our change in y, right? Your vertical change is your change in y. So I'm going to write that right here. This vertical change is delta y. Delta y. Now, what happens when, let's make this a pink line. And it's going to be the tangent line. It was almost good. It was almost good. Now it's perfect. Close to perfect. There's our tangent line. So we've got our tangent line. Look at our tangent line at x plus delta x, right? This is important right here. This right here is dy. dy. Now what's going to happen, hopefully you can envision this. What's going to happen is when your delta x and your dx becomes smaller, very, 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 very small, what happens? You know, the secant line gets very, very close to being the tangent line. It's not exactly the tangent line, but it gets very, very close to being the tangent line. So that's why we want that delta x to approach 0. So let's talk about the difference here between dy dx versus delta y delta x. Delta y delta x is actually on the secant line. So this is the slope of the secant line. Dy dx, that's the slope, this is the slope of the tangent line. And when our delta x approaches 0, when it gets very, very small, dy is going to be approximately the same thing as the change in y, delta y. And that happens, let's do this, when delta x or dx is very small. When delta x or dx is very small, then dy is approximately delta y. Okay, so everything gets much, much closer and the two values become very much the same, very much the same. Okay, let's do an example. Let's consider f of x equals x squared. We're going to compare the two values, and I'm going to show you how close they can get, how very close they can get. First, we're going to take f of x equals x squared. I'm going to graph that real quick. So I've got this curve here. It's a beautiful parabola, just half of it, because I just need the positive half, because we're talking about when x equals 1. I want to do that with a highlighter. When x equals 1 and dx equals 0.01. So when x equals 1, I'm going to have f of 1 as an output. And because we want to find the value dy, we're talking tangent line. So we're talking about the tangent line through that point. And we're talking about dx being 0.01. So 1.01 is my other input. So we're talking about that change right here. This change is dy. Versus, look at this, versus this slightly bigger, because look, the tangent line is underneath the curve, so 1.01 as an input would give you f of 1.01, just above this pink dot. So you'd have that pink dot, and you'd have, let's make it that baby blue again, and that blue one. So this blue one is going to be the actual delta. It's going to be your delta y. And this differential is going to be your dy. So here's your dy, and then your delta y. Then you're not going to have to do this every time. Your delta y is going to be just a little bit bigger than that, because it's going to have a higher output than your pink output. Excellent. I think you're following me. I'm hoping that you're following me because I'm hoping that I'm doing a pretty good job here. Okay, so let's write this down because if you're not following me, this will help. dy is the change on the tangent line. So it's your change in y on the tangent line. Delta y is your change on the actual curve. Actual is an important word there. Actual curve. I want you to be able to read what I'm writing. So dy is a little bit easier to figure out though, because remember, dy is equal to your first derivative times dx. So dy is going to equal to the first derivative, which is 2x. We're talking about this curve right here. So the derivative is 2x times dx. And now we just substitute in. I mean, this is very quick. No calculator. It's very, very simple. And that's what I like about calculus is that sometimes it can be associated with that word simple. So 2 times 1 times 0.01, which is 1/100th. So 2 times 1/100th would give you 2/100ths. That's what I'm talking about. No calculator. So our output here, this output right here is going to be 0.02. Now we expect delta y to be a little bit higher than 0.02. Well, how do we find delta y? Well, now we have to go back and do some non-calculus. So delta y, remember, is y2 minus y1. Right? It's y2 is f of x plus delta x. I'm going to write this down this first time. And y1 is just f of x. y2 happens to be f, which is x plus delta x, would be 1.01. X is 1, delta x is 0.01, add those two together and you get 1.01 minus f of 1. Now we have to go back in and we have to substitute it back into our calculator or into our formula, which has to use the calculator. So 1.01 times 1.01. Yes, we have the skill. We have the skill from elementary school to multiply that by itself, but we pick up the calculator because it's just easier to do that. So square 1.01 and you will get 1.0201. Then we have to substitute in a 1 for x and we get minus 1. Well, this subtraction I feel pretty good about. That's 0.0201. And that's what delta y is equal to, which is just slightly higher than dy. Now, why was it higher? That's because the tangent line was underneath the curve. The tangent line was underneath the curve. Check this out. What happens if the tangent line happens to be above the curve? Well, you're right. If it's above the curve, look at this. That right there versus maybe that right there. So that's when your actual is going to be a little bit less. So when is your tangent line below the curve? Your tangent line is below the curve when you're concave up. And your tangent line is above the curve, as demonstrated right here, when you are concave down. This is where the pieces just all start falling into place. You start putting everything together and your mind, it just blows up like one of those emojis. Okay, let's try this one right here. Let's compare. We want to compare dy and delta y, and we're given this function right here. We're told x equals -1, and delta x happens to equal dx, your differential, which is 1/10. Now, hopefully you can maybe hit pause and try this yourself, but if not, you can follow along. We've got dy, and then we're going to have delta y. dy is the approximate. This is your approximate change. okay? Delta y is the actual change. So dy is approximate because we're talking about the tangent line. Delta y is going to be the actual change according to the curve because both points are going to lie on the curve. So remember, dy is equal to your first derivative, which is 2x plus 5. All of that derivative times dx. And then dy is equal to 2 times negative 1 plus 5 times dx, which is 1/10. 3 times 1/10 is 3/10. This is the approximate change. The actual change is going to be, remember, it's going to be f of x plus delta x minus f of x. F of x plus delta x, well, x is negative 1 and delta x is 0.1. X is negative 1, delta x is 0.1. So without a I know I'm going to have to eventually pick up a calculator. I'm going to need to pick up a calculator, but I'm being stubborn. So when I'm stubborn, I sometimes make mistakes. $1 minus 10 cents, that's 90 cents, and then f of negative 1. That right there was risky because the first time I did this problem, I got it wrong. I'm not going to lie. So I would suggest picking up a calculator right now. F of negative 0.9. Remember, this is your f of x equals x squared plus 5x plus 6. Go ahead and put that negative 0.9 in for x. And you're going to get 2.31 minus f of negative 1 is 2. 2.31 minus 2 gives us a delta y of 0.31. Very, very close. That actual change is very close. So close that it was so much easier to use the calculus that's what we do. So much easier to use the calculus, right? Because on the right-hand side, algebra, you had to pick up a calculator. On the left-hand side, we didn't have to pick up a calculator. It's the same thing with finding extrema, when you're finding your maximums and minimums. So much easier just to find that first derivative, especially of a polynomial function. Find the first derivative, set it equal to 0, bada bing, bada boom, you're done. But on a calculator without calculus, you have to go to your calculator, you have to enter it into the graphing feature, you have to G-solve, you have to hit the max or min. If you don't have a calculator, you're kind of left to estimating. So this is why we use, one of the reasons why we use calculus. Okay, let's use differentials to approximate the change in revenue to an increase in sales of 20 units for this revenue function. Now I'm going to come back in the next video because we're going to do these 2 word problems, and then in the next video we'll do 2 more word problems. This way we're not completely overwhelmed by a video that just keeps going and going.